Okay, guys. Good morning. For as of now, for what we have completed, we have completed one and a half cycles. So today, we'll finish off the rest of the second cycle, and by the second week of October, we are having a midterm test. I hope you all are aware. So for that, we'll have 3 units. So with probably another 2 classes, we should be able to complete the third cycle also. So let's start with the class. You guys are able to see the screen?
Yes, sir.
I'll be sharing these contents also with you soon. Okay. So the second cycle, we have finished up the first part, which is the functions of ventilation, understanding the wind velocity and wind pressure, applicability of windrose diagram, and air movement around the building. This is what we finished up in the last class. For this class, so we'll have track-driven ventilation and pressure-driven ventilation. Examples of courtyard and wind tower. Humidity control in buildings where it's necessary. And then we'll have factors affecting airflow through buildings, pattern and velocity, orientation, external features, cross ventilation, size and position, and controls of openings. The last part I'll save it up for the next class because the software for demonstration, what I'll be used to is Autodesk Ecotech, which is not being currently available. It's become redundant. So I'll get you another software where we can do all of these simulations and get an analytical report of it. So we'll start off with humidity control. So here, with the humidity control, we have already spoken about humidity, and I hope you guys are aware of what we presently undergo with Chennai. Is a warm, humid climate, and we do have our discomforts with humidity. So there are 2 things normally it will be done. One is a dehumidification. That's a mechanical process where it would be done through condensation. Where what happens in a condensation? Any of you guys who are not on screen also can answer. Just unmute your mic. What happens in a condensation? Guys? You guys would have gone through the process, right? Condensation. What is condensation?
Sir,
Yeah, Gauri. Yeah.
the condensation is the process where the vapor changes, comes back into its liquid state. Liquid,
Yes.
yeah.
So once it comes in contact with a cold object, so what happens is whatever the air surrounding it, whatever moisture it's got, it will get deposited on the surface of the cold object. So this is what exactly we'll be doing in a dehumidification process. Whereas, as a humidity, why do we speak about humidity control is, there are places where we need to use humidity to control, as in like bring in thermal comfort. Example is Rajasthan, as I told you about hot, dry climates, where you can see all of these old palaces would be having a good, even though they are in very rocky mountains, you can see a lot of water bodies in them. They would have made fountains, ponds, lily ponds. All of these are small lakes itself. So these kind of water bodies are quite essential for them in the hot, dry climate places. For them, that humidity will bring in a evaporative cooling, as like any hot air passing through the water body would get itself cooled down and enters into the building. So this kind of feature is what we've been looking into right now. So what are these functions? Controlled air supply, filtering out sand and dust. So what is that they're speaking about the hot dry places is, normally in hot dry places, you have buildings with the smaller openings. You don't have very big openings. The reason why they have smaller openings is, once they want to use evaporative cooling as a method to bring in the thermal comfort, they don't want that evaporated cooled air to be moved out or sent out. So that's the reason most of these places, even for the retaining the cold air, the interiors have small openings. Another one part is all of these hot dry places have another problem of sand and dust. To reduce any sand and dust from outside to come into the buildings also, this factor plays in. So imagine this one condition, one climatic condition has brought in so many architectural features itself. And how is that evaporative cooling is used, that we'll see in this section now. So here there's an example which is given from Egypt where they speak about wind scoops. Wind scoops are nothing but tall towers in a building which will have openings on the top where the air will enter from the top of the building and go down into the section. So that is a section which is shown here. So here what they have done is they've got an opening which is towards the windward direction, which is on, imagine, not on the level of the other buildings, but this is projecting out separately. And this was towards the windward direction. So all this wind from here would enter in this place. And it is being passed through a pot. It's a porous pot where the water would be dripping from the top to the bottom. And they have a charcoal, layer of charcoal also being put. So water gets onto the charcoal. First thing is, charcoal is quite an absorbent material. It removes all the impurities from the air. And then this cold air, because the air has been cold and dense, it will obviously travel downwards. So we would have known about hot air rising up, whereas the cold dense air would be flowing down. So what happens is, here this water dripping and it's got a grate. Grate is nothing but a mesh. The mesh should have charcoal. The air would pass through the water, get itself humidified, cool down, and then moves out to the human activity zone. And there's a small pool of water that's for the dripping water to be collected here. In India, there is like another one method. As like I said about charcoal, there is another one organic material which is widely used in North, and even in South. It got cuscus. Here the spelling is CASCAS, but if you go on to Google, you have to look in for the spelling of CUSCUS. Cuscus, in Tamil we call it vetriware. Vetriware. I'll just show you a picture. So what you see here, these tall grasses, once they dried up, this is called vetriware. It's got a very good cooling agent property, as in water which is fused, it's got a cooling agent. Otherwise, this grass or roots by itself, it has got a very good absorbent quality where the water would be retained for a very long time, and any wind or breeze passing through these grass would get itself humidified and cool down. And it's quite organic also. It smells fragrant also. So here, this method is adopted in a lot of places in India. What they do is, in households, they would hang a mat of this cuscus grass. So, and there'll be water being, normally they won't drip it. What they do is they splash a bucket of water onto it, which should stay there for an hour or two. And probably after an hour or two, they'll again do the same. So this moist grass, what it does is, any hot air from the outside, which is flowing through, would pass through this mesh of mat, and then while it enters, it gets itself cooled down and brings in a good thermal comfort. So the advanced version of this is a very primitive version. The advanced version of it would be in Delhi. There was a desert cooler which has been developed. So desert cooler is something like a box which has got 2 feet by 2 feet, 600 mm by 600 mm on 4 sides. And what it got is, it would be something like desert cooler. It'll be like a conventional air cooler. I'm trying to get an image so that you guys have a better understanding of it. Okay. It's something like the one here on the front. So you guys are able to see this part, air cooler.
Yes, sir.
Yeah. So what it got is it usually is got surrounded by mats of cuscus on all the four sides, and there'll be a fan in the center, which is going to be placed in the center. And this boxes would have two trays, one on the top and another tray at the bottom. The top tray is a shallow water would be poured into it, and this water would drip onto the mat. And the fan, when it's pushing out the air, even while it's sucking out the outer air, it brings in through the mat. So that gets a natural cooling property, and this is kind of a air coolers. I'm really not sure whether this is the same one. Looks to be like that because you can see in this and all, you can see these mats on the side. So this is pretty much the same one. So these kind of coolers are being used for humidification. These are all processes that are done for to humidify a place. So this is what being described all across in this. And the pumps would, what they do is once the bottom tray gets filled up, the pump on the air cooler would take the water back onto the top tray, and again the process continues. So this is about the humidity control, as in like how in different places the humidity plays a role in bringing in thermal comfort. Just a minute. Now we go on to the provision of ventilation. That's stack effect. So I hope you guys would have heard about stack effect, but still I tell you, stack effect is nothing but it uses the principle of the temperature of air and what happens to the properties of air. So when the air gets hotter, heated up, the water tends to be less dense and it starts to rise up, it flows up. And a cool air, which is much more denser, would always stay low. So this principle is used in buildings to bring in a comfort level. So most of the courtyards does that. So what happens is in courtyards and all of these, the courtyards would have rooms on all sides, and these rooms would have openings, windows. So when the courtyard is given a provision where it's going to get heated up and the hot air from that particular part gets heated up and rises up, so it obviously has to replace the air from the lower level. So which brings in the cold air through the windows and replaces onto the place. So this, if I can show it to you, these sections. Sorry, the image size is too small here. Sorry for the clarity, otherwise I'll probably get you. Okay. You guys are able to see this drawing here? What happens here?
Yes.
Yeah. So this drawing here, it shows the courtyard where the centralized part, where which the habitat is going to be there, where it gets heated up, and here the hot air rises up. As I told you, once the air gets heated up, it tends to loosen out and it's going to be less denser. So it obviously tries to move up. That's one perfect example is you can see how the steam rising from a cup of coffee or a boiling water. That's pretty much the same principle. And what happens is because this hot air leaves here, this leaves the spaces with the less pressure, which means it obviously brings in cold air. Whichever cold air is lying on the lower region of the buildings would be brought through this part. So here there are various examples of it, various representations, how courtyards can be used with that. So how this stack effect works on it. So this principle is widely used in a lot of our earlier buildings where there are various configurations. If if you can see this, in this one, there's going to be a small opening at the bottom and there's an opening vertically up. Whereas you're right at the bottom and it goes straight up. You're between the slabs. You're between the floor slab and the roof slab. So there are multiple configurations of this are used to bring in thermal comfort. In example, the older houses, if you see, they'll have a double-story eye. Even churches have these examples of double-story eye, and there will be glass windows on the top, the openings. So these all enable the stack effect to function there. So ventilation ducts and arrangement. So here we saw about the airflow around the building in the last class. And now what you're going to look into is airflow through the building. How the openings can be manipulated and how the building is going to respond to this. So normally to test out all of these airflows, the methods to be used by people earlier to derive the results, that was an open jet wind simulator. So this is going to have a fan which is going to throw in air inside, and here there are just going to be paper strips hung on here just for it to smooth out to reduce the turbulence of the air, and there will be a model placed at the end. So this shows whether the wind has got a laminar. Laminar flow is nothing but a smooth flow. It's going to have a turbulent flow. So this is an open jet type. Guys, someone's mic is on. It's bringing in interference. Much better. Can you please mute your mics? If you have doubts, please unmute and ask. That's not a problem. So in the closed wind tunnel test, that's an open air jet flow. Now there is another method to do the same thing. But here, rather than the air being actually thrown into the building, what they do is they use smoke. They leave smoke at one point, and there'll be a fan on the other end, which would be retrieving. So the fan would be almost working like an exhaust, where it would be pulling out the air, and this would go through this part, which will go funnel above the building or on the sides. So this way they'll be able to judge where the laminar flow of smoke goes through or not. So consider all of these tests are done through a building or blocks which are totally solid. They don't have any openings. So now we'll see how these orientation and the openings work with. Those are two methods in which these factors can be tested out. So that's just the information. You don't need to really work on the logic behind that. So how is that orientation going to work? So the greater, I'll just read out the first line here. The greatest pressure of the windward side of the building is generated when the elevation is at right angles to the wind direction. So what they try to say is, if there's going to be a wind flow coming through, the greatest pressure would be on the surface on the right angle. The wind flows here. This is the surface of the building, and it's whatever is going to be on the right angle. This is what is going to get the maximum pressure. Maximum pressure is nothing but, imagine you're riding a two-wheeler, and when we are riding through it, we are going to get breeze through our face, breeze at our face, and that's the pressure. That's like we call it a wind flow, or we call it wind pressure. So this pressure, once only if it's right at right angle, it gets a maximum. So what happens when if it's hitting at an angle of 45 degrees? Only 50% of the pressure is obtained in that. So this is what this observation is pointing out. So here there is a small mapping of how this pressure difference varies. When you have a very small opening on one side and a bigger opening, 44% of wind pressures are observed. Another time, when you have a bigger opening on the other side and a much more bigger opening on this side, you have the pressure gets reduced because most of the air is going to penetrate in. Here, only a small amount of air is penetrating in. Here, this pressure again increases here in this stage because there's no obstruction at all. Whatever is being received, there's no condensation, nothing at all. It's going to relieve almost the true value. So this happens as the same for 45 degrees of orientation, how this angles vary. And this is one important diagram that you guys need to understand with whatever experiment I said, what it is. So this square box on the top here, I'm speaking about this square. You guys are able to see this blue. So that's a building what you're looking into. And as I told you, the wind pressure is at the right angle to the building. What happens here is, because this solid box doesn't have any openings, so obviously the wind will be diverted to the either side. And what happens is, once it goes here, this part, I'm not sure you can see where I'm highlighting. You guys are able to see this blue box here in which I've highlighted?
Yes, sir.
Yeah. So because this part doesn't have any opening and the wind is obviously diverting up, this becomes a high pressure zone and the wind is flown around. And what we see as this arc, as the greater A, is nothing but the wind shadow. Wind shadow is nothing but the place where you don't get any air movement. So this is at the bigger spot. So this is how it happens when the building orientation is at the right angle to the wind direction. Now we see on to another case scenario where the building is at rotated at 45 degrees. And how is it going to react? Now, the wind flow is at the right angle from this side. With the 45 degrees, it takes a much more bigger arc. And what happens here is, when you compare these two diagrams, this brings in a much more bigger wind shadow. You get the point? So now, why are we speaking about this orientation part is, imagine you're placing multiple buildings in a site. So next thing is, what you should do is, if at all you're having a building which is 45 degrees oriented, then you must place another 45 degrees oriented building somewhere around here and not right behind it. If you place it right behind it, it will fall into the wind shadow region and you won't be able to bring in any natural ventilation into that building. You guys are clear? Guys?
Yes, sir.
Yeah, fine. So effect and direction of the wind shadow, that's what is being said. And there is another one important point, yes. This para is quite important. It often happens at the optimum solar radiation and the optimum wind orientation. It often happens at the optimum solar orientation. Optimum solar orientation is the minimal solar side. And the optimum orientation, where the solar gets a minimum impact to the building, and the optimum orientation of the wind do not coincide. As in, if you want to be really orienting your building with the aspect of solar, sun, you have to look into few criteria. Normally, we'll say, we'll try to use a minimal side of east and west, because that's where we get a heat gain. If we look into the solar orientation, you guys are able to relate it. If at all you want to be thinking of just solar and you want to make your building much more safer from the heat, you'll have a comparatively smaller sides on the east and west. But if you look into the wind directions of the same region, the wind penetration would be more on the east and west direction of the buildings. So how you're going to manipulate and manage both of these is what is being mentioned here. It doesn't always go inside. And the next part. Now we go into the cross ventilation. Cross ventilation is best explained. Have you guys tried this experiment of you have a mug or a tumbler, an empty one, and try to put it on the try to immerse the open side onto a bucket of water? Have you guys tried out any experiments like that? Would you be able to push through the vessel inside? Guys?
No, sir.
No. Okay. So normally what happens is a empty tumbler, if you try to push the open side flat down with into the water, it could be a pond or a bucket or anything, into water, you would need to put extra pressure to push it in. But even though you push it in, the space, the void inside the cup remains empty. The reason is because it is already trapped in air onto it. So which means it won't allow any water to get into the place. Similarly, in a building, what happens is, do you see this example here?
Yes, sir.
This first diagram. So what you see is this building, this is on a section. There is an opening on one side. There's no opening on the other side. So which means what happens is, again, this part of the building is filled up with air, which is already there. And there can't be any new movement of wind or air into that building. So what it does is the air enters, it rotates here and moves out. And again, it envelops the building. With this, this is a lack of cross ventilation because there's no opening at all here because it's already occupied. Similarly, there's another example here. You won't get the movement. So here is an example of how these cross ventilations work. Normally, what is cross ventilation is, we say there are two openings on the parallel side of, it could be on a parallel side or it could be on the perpendicular side also. That's not a problem. But there should be some part, how it's going to be taken up. So what happens here is, in this building, unlike the earlier part, this got an opening at the top level on the left side, and this got an opening on the right side also. So what happens? This air movement, air would enter here, replace all the air in the top and exit out. Do you see this part at the bottom? Here, as I told you, there won't be any movement of air because the point in which it enters and the point in which